Hello everyone, to our next session. And this one we're going to be talking about enhancing ship design for advanced 3D workflow integration. And our speaker is Mikko, who is EVP for Design Solutions at NAPA. Over to you.
Thank you very much, Jake, and hello to all listeners. And thank you also so far for the brilliant presentations. I'm not sure if it's any more possible to up the game, but let's try. I will talk today about enhancement of ship design through advanced 3D workflow integration. Uh, I will first talk a little bit about the current and future maritime landscape and some of the challenges that are associated to ship design process to stay competitive in this rapidly changing market environment. We will then look at the concept of integrated 3D workflow and deep dive into three different example use cases uh, before we finally then conclude the presentation. Maritime industry is being shaped at the moment by the forces of energy transition and also global security, as we know. And I think it's fair to say, if we look ships of tomorrow, that they will be quite different than ships of today. Uh, if we, for example, talk about the uh, alternatives and the range of energy configurations that there is available today, there's so much variation compared to the past. Also, connectivity is not an issue anymore thanks to availability of high bandwidth satellite-based internet connection. So the vessels of tomorrow will be smart, connected by default. I think it's also evident that the level of complexity in design is growing due to new type of requirements that the energy sources and smart connected vessels are bringing to design. We've already witnessed several evolutions of shipbuilding process innovation, but I think the industry is again about to take the next leap in the evolution, as many shipbuilding companies are today looking to streamline their whole process from early conceptual design all the way to manufacturing and delivery. And we've already seen many inspiring presentations about smart shipyards and digitalization in this conference. Paradigm shift towards integrated 3D methods in early design uh, is something we have already witnessed, and we are seeing that it's accelerating actually. Another hot topic at the moment in the industry is 3D based approval of hull structures. We will talk a bit more about that today. Um, Shipbuilding specific product data management and smart shipyards. That's also a topic that is very interesting and topical today, and we already saw many interesting presentations about that. Uh, Digitalization and all the technologies like AI, of course, open now whole new level of possibilities to improve the efficiency and competitiveness. While there are possibilities, there's also challenges. First of all, shipbuilding is a time-critical business where design activities are part of the lead time of manufacturing of each product. So it's so-called engineered to order type of a business. So there's a need to achieve optimal design within a short delivery time. And multidisciplinary design and concurrent engineering is creating challenges of its own. And in this space, later phase design changes can be expensive to fix during the manufacturing phase. If we talk a little bit about the data management, still today many of the systems are non-integrated, and that hinders collaboration, data flows, and total design optimizations. At the same time, this can lead to inconsistencies between different software systems on the design data that can lead to errors, delays, and increased costs. So data-driven decision making is not yet fully achieved. There are also some external challenges like cyber threats. We have seen many cyber attacks in the maritime space. IP protection, it's always really crucial in shipbuilding. And also, perhaps there is some level of digital skills gap what comes to the adaptation of new type of technologies and methods. Let's go a little bit into details about these challenges, and I'm using now a very generalized and simplified representation of a design process to illustrate some of the challenges with the information flow. 2D drawings, they are used today to large extent to represent, share, and manage design information, and I think there is a good reason for that. Drawings offer often the needed information at glance, and the production of 2D design information is easy to scale, distribute, and predict. At the same time, various 3D models are being used to represent the same design information which is in the 2D drawings, while different data management solutions are being used to capture and organize the essential information to serve the overall project execution. One challenge is that there are disconnections between data flows, between systems, between 2D and 3D, between 3D and data management, and this means that the design information needs to be manually duplicated and replicated in many systems, and that is creating inefficiencies and uh, possible errors and duplicated data. And when this is multiplied throughout the process, it can be a real inefficiency. Okay, let's take another look of our simplified generalized design process, this time applying the concept of so-called integrated 3D workflow, what we have been here at NAPA very much studying and exploring. In the integrated 3D workflow, so-called master model can be used as a main branch of the process. And this master model is used to design the key vessel characteristics in the initial design phase, such as stability, capacities, performance, arrangement, and so on. But this same model can actually carry the design information all the way to basic design phase to handle the approval and all the way to detailed design. And through seamless integrations, it's possible to continue in production design using the same master data. The information and data from the master model can be connected to your choice of data management solution to serve design revision, collaboration, and early phase production planning. 2D drawings are, of course, still very important piece of assets during the design process, and utilizing this enhanced integrated 3D flow, 2D drawings can be extracted anytime from the master model while maintaining the connection to the master data. This is now, of course, very idealized and high-level general representation, but let's dive next to three different example use cases of integrated 3D workflow. The first one is called operational simulation. And if we think about how to future-proof the design in the current market environment, where it's important question to understand the carbon emissions throughout the life cycle of the asset. This is a tricky question because there are a wide spectrum of energy configurations to choose from. There are different type of energy appliances like wind propulsion, which you can take advantage of, and there are different type of indicators to calculate the carbon rating of the design or the vessel during the operation. And at the same time, of course, while making the design, you need to still ensure that your stability margins are within the range. The design is safe. For example, some fuels are really toxic, and how about the capacities? The energy density of alternative fuels can be much lower than conventional fuels, and so on and so on. So, how to validate the viability of design over the life cycle in real operating conditions? Well, one promising concept is now operational simulation. So when we take the initial design space and we utilize this integrated 3D workflow, master model, naval architecture calculations, and strength assessment, and couple that with operational data, uh, historical voyage data of the existing world fleet, together with the hindcast weather data and route optimization, we can actually simulate operating conditions in design. And this can provide valuable insights to support the decision making in energy system selection, to analyze the impact of energy saving devices, to conduct the holistic performance optimization, and to understand the life cycle CO2 emissions. In this particular case study, the objective was to study two alternative fuel designs of bulk carrier for iron ore trade between Brazil and China. And the consideration was especially the fuel tank sizing and the implications of that. The first alternative was methanol and LSFO fueled one, where the part of the cargo space and ballast water tanks were used for the methanol storage. And the second design alternative was LNG and LSFO powered, where the LNG tanks were located on top of the aft deck. And real voyage data was used in this study to analyze the configurations. The insights of this kind of study can reveal the following items. First of all, it was interesting to compare the operating mode distribution of these alternative designs against similar ships on the same trade pattern. And this study revealed important information that helped with tank and engine sizing based on simulated voyages in actual weather conditions. And it's possible to use the data from this kind of study to estimate the carbon rating of each design variation on a simulated operating profile. And while doing all this, of course, the basic naval architectural aspects could be handled at the same time, like stability, margins, and capacities, and overall arrangement of your design. Next, I would like to talk a little bit about integrated strength assessment. And here let's take an example case of a strength assessment of medium-sized tanker. If we look at the conventional strength assessment of this type of a vessel, it can mean anything between 1 to 2 months in calendar time. And basically the process is such that from the initial design phase, uh, the information is used to create some initial structural drawings so that the prescriptive rule checks can be calculated either by utilizing class software or perhaps Excel spreadsheets. Uh, and after that, a finite element model can be created for direct strength assessment according to the common structural rules. And this is actually the most time-consuming part of the process. And after that, drawings can be updated, and uh, the hull structure weight can be estimated from the drawings. But there are some challenges here. First one is the time limitation. It's challenging to optimize the hull weight during a very limited time slot available in this initial design phase. And the estimation method of hull weight is typically relying, therefore, on statistical and historical data. And actually, a large amount of the time is going here to select reasonable scantlings that fulfill the requirements. If we now look the same process by applying this integrated strength assessment approach, we can first of all start the process by utilizing our master 3D model. So the compartment model from the initial design phase can be taken as a basis where we can apply automatic structure modeling using parametric methods. And when we apply parametric methods for the model creation, that actually enables quick design changes. It enables design optimization and so on. So using this automatically generated parametric structure model that is connected to the master model, it's possible to quickly run finite element meshing, set the load and boundary conditions, and conduct the finite element as analysis and optimate and iterate this so that the results satisfy the requirements. After that, the buckling calculation can be conducted again using the same model. And weight is of course something that comes automatically out of 3D model for each and every design variation. So precise weight estimate is always at hand. And this whole process can be run in a loop that can help to find the most optimal configuration. Some benefits of this process is that it's possible to find optimized sizing of tanks and structures based on these automatically generated design alternatives. So basically in less time, it's possible to analyze and study more design iterations and have accurate hull weight estimation for each variation. Also, the outcome was that there was a substantial person hour reduction after the process was set up, thanks to this automated and parametric approach. So all in all, this approach can help to achieve optimized design with lighter hull weight that can increase competitive edge. A few notes about this type of an approach. This particular example is now about fully automated process, and there is certain initial effort of developing and setting up this type of a process. It depends, for example, what is the ship type you're dealing with, what is the class society in question, and so on. But also so-called midway solution using off-the-shelf tools, minimal cost customization, minimal configuration can provide significant benefits versus the conventional method. So if you just couple 3D CAD with automatic FE meshing, there's already one area to make gains, or coupling 3D CAD with class society prescriptive rule checks. Then let's talk about the third case, and that's 3D model-based approval. 3D model-based approval in a nutshell is a concept of utilizing 3D models for conducting class approval of hull structures. At the moment,
just to let you know, Mikko, we've got a couple of minutes left, so yeah, happy for you to run through this one.
Thank you very much. Thank you very much. Try to speed up. Yeah, at the moment, class societies, shipyards, and CAD vendors are working to realize effective 3D model-based approval process. There are different drivers for different stakeholders to go into 3D approval, but maybe if we speed up a bit, there are still some considerations like what is the data compatibility and consistency, how to easily manage design review, and how to maintain IP protection. If we look about data compatibility and consistency in a conventional process, there are manual data entries between 2D drawings, 3D CAD, FEM software, and class software, and intermediate files are used for data exchange, and that can create inconsistencies and errors. But this integrated process using 3D CAD and class software together through API integration can solve this one. Second one is ease of design review. Again, using the master model, it's possible to handle real-time communication between designer and class through efficient commenting tools and using informative 2D, 3D hybrid representation of the design information and model. Third solution here is to ensure IP protection, and there is technology available that enables collaboration across stakeholders without, let's say, a risk of losing the data for unwanted parties. So there are encryption technologies and web-based viewer technologies where the data is being hosted at the shipyard, who can control the access rights, can manage and solve this challenge. Then let's go into conclusions. So we discussed about the process innovation and how that is the key to maintain competitive edge in the changing business environment. And integrated 3D workflow is one potential method to gain efficiency in design process. We covered three different use cases. First one was this operational simulation that is a promising concept to minimize carbon risk. Second one was integrated strength assessment and 3D CAD that can substantially boost structure design efficiency. And finally, we touched 3D MPA process. It is possible to improve quality, traceability, and time to market with secure 3D model-based approval process. Thank you very much for your attention.
Thank you very much. Great presentation, and yeah, fully buy in and agree with the concept of reducing the kind of interactions between models, because that always is the biggest time sink in the design process. One very quick question, if I may. You kind of hinted at it through your presentation, but is the idea, do you reckon it's feasible to have kind of one single all-purpose 3D model throughout those different stages, so that you can have one central kind of point of knowledge?
I think that's a fair question, and it really depends what is your current starting point, what is your CAD system setup, what type of vessels and projects you are dealing with, and my advice is to identify the, let's say, bottlenecks and inefficiencies, and then try to utilize this master model concept for those areas first. That's where you can make most gains with reasonable effort.
Brilliant. Well, thank you very much again for your time, and on to the next session. Thanks again.